In the last video, we learned about how to draw a Lewis structure for the neutral simple molecule. In this video, we are going to work on drawing Lewis structure of charged molecules and calculation of formal charges. Let's work on silicate anion and draw its Lewis structure. If you remember from the previous video, the first step was counting number of valence electrons for the molecule. This molecule is made of silicon and oxygen. Silicon is in group 4, so it has 4 valence electrons. Oxygen is in group 6, so it has 6 valence electrons, and we do have 3 of them, so overall 18 valence electrons. The negative charge here means we have an anion. And when we have an anion, that means we have an additional electron in the molecule. Here the anion has 2 minus charge. Therefore, we have 2 additional electrons in the molecule, and we need to add them to the total number of valence electrons. So 2 additional electrons. Therefore, the total number of valence electrons would be 24 valence electrons for this molecule. The next step is determining the central atom. If you remember the electronegativity trend in the periodic table, silicon is less electronegative than oxygen. So silicon will be the central atom here. And then we need to connect the surrounding atoms, oxygens here, to the central atom with a single bond. So we have 3 oxygens in this molecule, and we will connect them to the central atom with a bond or stick or lines. Each bond accounts for 2 electrons. We have 3 bonds here, so overall 6 electrons for making those bonds. Therefore, we used, so overall 24 valence electrons. We use 6 electrons to make bonds, and the remaining electrons will be 18 remaining electrons. The next step is distributing the remaining electrons to the external atoms to make them octet. So let's do it together. I start with the oxygen in the right side. So 2, 4, 6, and this bond gives us another 2, so overall 8 electrons around the oxygen. So oxygen is octet. I already used 6 electrons, so 8, 10, 12. This oxygen is also octet. 14, 16, 18. So all 3 oxygens are octet here. Now let's take a look at the central atom. So the central atom has 2, 4, 6 electrons. It is not octet. In this situation, one of the oxygens will share the electrons to the central atom and make a double bond. So this oxygen only shared the electron with the central atom. So it is still happy an octet. Now, if you count the electrons around the central atom, we have 2, 4, 6, 8 electrons. The central atom is also octet. You may ask, which oxygen can do the sharing? The answer for this question is any of these 3 oxygens can share the electron with the central atom. For example, this oxygen can also share the electron with the central atom. We call these two structures resonance structures, and you will learn about the resonance structures later on. So the fourth step is recounting electrons in the molecule and compare them to the number of valence electrons that we calculated in the first step. So we have 2, 4, 6, 8 electrons, 10, 12, 14, 16, 18, 20, 22, 24. The number matches this number. So this is an acceptable structure for the silicate. Now, the question here is how can we show that -2 charge on the molecule? This is the place that we need to introduce formal charge. So formal charge is number of valence electrons for the specific atom the atom that we are calculating formal charge for, minus number of bonds or sticks around that atom, minus number of electrons in the lone pairs on that atom. So pay attention. Here we are subtracting the number of electrons on the lone pair. So I would like to draw a chart here. So number of valence electron, number of bonds, number of electrons in lone pairs, and formal charge. So this oxygen right here, I call that oxygen number 1, oxygen 1. So this oxygen right here. Oxygen has 6 valence electrons. You'll see one bond connected to that, -1, and it has 1, 2, 3 lone pairs, and each lone pair has 2 electrons, so overall 6 electrons. Therefore, the formal charge for this oxygen would be -1. For this oxygen, because it's in the same condition, I call that oxygen 2, the formal charge would be the same. Now for oxygen number 3, it has 6 valence electrons. You'll see 1 and 2 bond connected to that, and number of lone pairs, 1 and 2, each has 2 electrons, so overall 4 electrons. The formal charge for that oxygen would be 0. Now, the formal charge for silicon. Silicon is in group 4. It has 1, 2, 3, 4 bond connected to that. And it doesn't have any lone pairs, so 0. 4 minus 4 minus 0 gives us 0. So if you look at this calculation, we have 2 -1 formal charges on this molecule. That means molecule can carry 2 minus charge. When you learn about the resonance, you'll see that -2 charge spread on the whole molecule. But for now, this is how we assign formal charge for a single atom in the molecule. Another use of formal charge is helping us to determine the best Lewis structure for a single molecule. Here you see 2 possible structures for hydrogen cyanide. Let's calculate the number of valence electrons for hydrogen cyanide first. Carbon is in group 4, so it has 4 valence electrons. Nitrogen is in group 5, it has 5 valence electrons. And hydrogen has only 1 valence electron. So overall, it should be 10 valence electrons. So, molecule in the left, it has 2, 4, 6, 8, 10 valence electrons. Molecule in the right, 2, 4, 6, 8, 10 valence electrons. So both molecules have 10 valence electrons. Now, let's see if all the atoms in these molecules are octet. So 2, 4, 6, 8 electrons around this carbon, it is octet. 2, 4, 6, 8 Nitrogen is also octet. Hydrogen has only 2 electrons, and remember, hydrogen can only make duet, so it's good. Molecule in the right, 2, 4, 6, 8. Nitrogen is octet. 2, 4, 6, 8. Carbon is also octet, and hydrogen has its duet. So both molecules are also got their octet. The tool here that can help us to figure out the best structure is the formal charge. So if you remember from the previous video, formal charge equals to number of valence electron on a specific atom minus number of bonds connected to that atom minus number of electrons in the lone pairs on that atom. Now, let's draw a chart for each molecule and calculate formal charges for each atom in the molecule. So, number of valence electrons, number of bond, number of electrons in the lone pairs, and formal charge. So, for carbon has 4 valence electrons. In this molecule, carbon has 3 bonds and it has 1 lone pair, so overall 2 electrons for a single lone pair. Therefore, the formal charge would be -1. Nitrogen is in group 5. It has 1, 2, 3, 4 bonds, 0 lone pair, so 5 minus 4 minus 0 gives us +1. Hydrogen has 1 valence electron. It has 1 bond connected and 0 lone pair gives us 0 formal charge. Now, for the other molecule, we also need to calculate formal charges for all the atoms. So, number of valence electron, number of bonds, number of electrons for lone pairs, and formal charge. Carbon, group 4. Here carbon has 1, 2, 3, 4 bonds and 0 electrons, 0 lone pairs. So 4 minus 4, 0 minus 0 gives us 0. Nitrogen, group 5. And we'll see 1, 2, 3 bonds connected to that. And we have 1 lone pair on the nitrogen. So 2 electrons, 5 minus 3 minus 2, 0. Hydrogen, 1 valence electron, has 1 bond, 0 lone pair, 1 minus 1 minus 0, 0. So the rule here is minimal formal charges are the best. So between these two structures, the best structure is the structure in the right, because all the atoms in the molecule have 0 formal charges. Also, in this structure, carbon has -1 formal charge and nitrogen has +1 formal charge. And we know that nitrogen is more electronegative than carbon, So it would be better to have negative formal charge on the more electronegative atom. Based on these two reasons, the structure in the right is the best structure for hydrogen cyanide.